In this set of notes, we're going to continue looking at functions that have two or more independent variables. So to start out, we're going to look with functions of two variables, and suppose that we want to know how the function f of xy changes when x and y change. Instead of changing both variables simultaneously, we might get an idea of how f of xy changes depending on x and y when we change one variable while keeping the other one fixed. And we can do this by looking at what is called the partial derivative. And here we've got the definition of what a partial derivative is, and you'll notice that it's very similar to the definition of a derivative we've seen before. The only difference is now instead of having f of x, we have f of x and y. And so if you'll remember previously when we talked about that derivative, we have the limit where essentially what we're doing is we had the space between x and x plus h, so that difference being h, and we were looking at the limit as h went to 0. So notice here when we define a partial derivative, what we're doing is when we take the partial derivative of f of x, y with respect to x, we're only increasing x by h. Or if we take the partial derivative of the function with respect to y, we're only increasing in the y direction by h. So again, very similar to what you've seen before. So let's look at a couple examples of what these partial derivatives look like. So to start out here, we have a function of x and y, and here that function is equal to 2x divided by y minus 3 divided by xy squared. So there are two different partial derivatives we can take. We can take the partial derivative with respect to x, or the partial derivative with respect to y. So let's start with the partial derivative with respect to x. Now, when we take the partial derivative of a function, very similar to our notation before, we have the function on the top and the variable we're taking the derivative with respect to on the bottom. The difference is previously when we have one independent variable, you would see a d. When we take partial derivatives, we typically use the notation that is called curly d, and it goes by other names as well, but it's just like what it sounds like. It's kind of a curly d. All right, so let's take the derivative of f of xy with respect to x. Now, when we take this derivative, what we're going to do is we're going to treat all variables other than x as a constant. So here, I'm just writing out what my function is. And let's just highlight where x occurs in this function. So we have an x here, and we have an x here. So when we take the derivative, we're going to treat everything else in this function as a constant. All right, so starting out, the first thing I'm going to do is I know by derivative rules that we've seen previously, I can go through and the derivative of the sum is equal to the sum of the derivatives. And again, everything that is not an x, we're going to treat as a constant. So looking at the first term, 2y is a constant, so I'm going to pull that out front. And looking at the second term, 3 divided by y squared is a constant, so I can pull that out of the derivative. All right, we know that the derivative of x with respect to x is just 1, so the first term is just 2 divided by y. And looking at the second term, this is the same as x to the negative 1 power, so we can use our power rule. So we have our constant out front, and then applying that power rule, we're going to have minus 1 times 1 over x squared. And so this becomes 2 divided by y minus 3y squared, but we're multiplying by a negative 1, so that becomes positive, and then the x squared is also in the denominator. Now this is that partial derivative with respect to x, and so again, notice when we take the partial derivative with respect to x, we treat y as a constant. We could also take that partial derivative with respect to y. And so notice if we're going to do that, this time we're going to treat everything that is not y as a constant. And so again, just to help myself out, I'm going to highlight where those y's are, and everything that is not highlighted is going to be treated as a constant. So looking at the first term, notice my constant piece is going to be 2 divided by, my constant piece is going to be 2x, and so I'm going to be taking the derivative of 1 over y. So similar to what we did before, we're going to have that power rule. So this is really y to the negative 1, so I'm going to have negative 1 times y to the minus 2, and then multiplying by that constant, which is 2x. Looking at my second term, my constant piece is going to be 3 divided by x. And then here I really have y to the minus 2, so again using my power rule, I'm going to have minus 2 times y to the negative 3. And so notice this is equal to 2x over y squared plus 6 over xy cubed. All right. So let's look at another example. So again, we're going to find the partial derivatives of this function. So the first one we're going to find is we'll find that partial derivative with respect to x. And so this is going to be equal to the partial derivative with respect to x of x squared e to the x plus 2xy. So if we're going to find the partial derivative with x, so again I'm going to highlight where my x's are. Notice here that I have two functions that involve x. I have x squared and I have e to the x plus 2xy. Since I have two functions here, I am going to have to apply the product rule because I've got, again, two functions multiplied by one another. And then also notice that I have e to the x plus 2xy. So I know I'm also going to have to use the chain rule. So by the product rule and the chain rule, we have the following. So looking at the first term here, I have x squared. So if I take the derivative of x squared, that's going to be equal to 2x, and then I multiply that by the second function. So applying that product rule, plus the first function times the derivative of the second function. So my second function, I have e to the x plus 2xy, and we know the derivative of e to the x is e to the x, but then I need to multiply by the derivative of the inner function, which in this case is x plus 2xy, and I'm taking the derivative of x plus 2xy with respect to x. So the derivative of x with respect to x is 1, and that second term, 2xy, remember that we're treating the y as a constant, so that is just 2y. So simplifying, this becomes e to the x plus 2xy times 2x plus x squared plus 2x squared y. Just like the previous example, we can take the derivative with respect to x, or we can take the derivative with respect to y. So again, notice I'm using those curly d's, and so this is going to be equal to the derivative with respect to y of x squared e to the x plus 2xy. And so again, just to help myself, I'm going to highlight where the y's are. So notice here we only have one y, and that's in the exponent. So here we do not have two functions of y that are multiplied by one another, so I'm not going to need the power rule. This time I'm only going to need the chain rule. And this is because that x squared, we're going to be treating that as a constant. So this derivative, we've got that constant x squared. We're going to multiply that by e to the x plus 2xy. And again, that's because we know the derivative of e to the y with respect to y is just e to the y. And then we need to multiply by the derivative of that inner function with respect to y. So the derivative of x with respect to y is just 0. Again, x is a constant here. And then the derivative of 2xy with respect to y is just going to be 2x. So this is going to be equal to 2x cubed times e to the x plus 2x y. Now, we're not limited to only looking at two variables. We can look at more. I should note here, I have a note that your book looks at the geometric interpretation. So previously when we worked with a single independent variable, we saw our geometric interpretation of the derivative as being that line. Here, your book goes through a good discussion with images of the geometric interpretation of the partial derivative, so I do recommend reading that section on your own. So moving to the function with more than two variables, if we want to take the partial derivatives here, again, this is going to be pretty straightforward. We're pretty much just going to do the exact same thing we did. Notice here we have a function of x, y, and z, so this means that there are three partial derivatives that we can find in this case. We can find the partial derivative with respect to x, the partial derivative with respect to y, and the partial derivative with respect to z. So notice the partial derivative of f with respect to x. To make this a little bit easier on myself, I am going to go ahead and multiply through that xy. So notice both terms here involve the x. The y and the z are going to be treated as constants. So the derivative with respect to the x of the first term is just yz, because y and z are constants. And the derivative with respect to x of the second term, using the power rule, is going to be 2x y. And again, the y is there because we're taking the partial derivative with respect to x, so we're treating y as a constant. Well, you could take the derivative of the function with respect to y. So again, doing the same thing, looking at the first term, we're taking the derivative with respect to y, so x and z's are going to be constants, so that just becomes xz. Looking at the second term, the x squared is a constant, and of course the derivative of y with respect to y is just 1. And then finally that partial derivative of the function with respect to z. Notice in my first term the x and the y's are constant, and then of course the derivative of z with respect to z is just 1. And then the second term doesn't involve a z, so for that reason that is just the derivative with respect to z of a constant, which is just going to be 0. So here are those three partial derivatives. And if we had a function of 4 or 5 independent variables, we would go through the same process. We can also take higher order partial derivatives. So as in the case with functions of one variable, we can define higher order partial derivatives for functions of more than one variable. So for instance, to write the second partial derivative with respect to x, what we would do is we would first find the first partial derivative with respect to x, and then take the derivative of that partial derivative with respect to x. And we can also compute mixed derivatives. So for example, we could compute first the partial derivative with respect to x, and then compute the partial derivative with respect to y of the first derivative. And so let's look at two different partial derivatives of that function that we saw before. So let's first recall from the previous page that we already found that the partial derivative with respect to x, with respect to x of the function is equal to yz plus 2xy. So let's say that we wanted to find the second derivative, or the second partial derivative with respect to f of x. And so this notation means that we would find the first partial derivative with respect to x and then take the partial derivative with respect to x again. So since we already have that first partial derivative with respect to x written up top, we now just again need to take the partial derivative with respect to x. Notice that the first term yz does not involve x, so it is just a constant, so that the derivative of that first term is 0, plus in the second term 2 and y are the constants, so this just becomes 2y, because the derivative of x with respect to x is just 1. Another higher order derivative that we could look at is we could take the second derivative of x first by taking the partial with respect to x and then the partial with respect to y. So in this case, we still start with that partial derivative with respect to x. So here we have the yz plus 2xy. Then we take the derivative of it with respect to y. So looking at the first term, we have yz. So z will be a constant, and so taking the derivative of that with respect to y just gives us a z. Plus, in the second term, our 2x is going to be the constant multiplied by y. Well, the derivative of that with respect to y is just going to be 2x. So what happens if we reverse the order of the x and the y? Well, on the previous page, we just computed this second derivative, so let's just write it down. So what if instead we had first computed the partial derivative with respect to y and then the partial derivative with respect to x? Well, recall that we already found that first partial derivative of f with respect to y, and we found that on the previous page, well, 2 pages back. And so we have that one right here. So that's going to be xz plus x squared. So now let's find the partial derivative of that with respect to x. And notice we're going to get here, looking at that first term, z is going to be the constant, so we just end up with z. And the second term, the derivative of x squared with respect to x by the power rule is 2x. And so notice that first we found the partial derivative with respect to x and then the partial derivative with respect to y, and we got z plus x, 2x. Next, we found the partial derivative with respect to y and then took the partial derivative with respect to x, and we got the exact same thing. In both cases, we got z plus 2x. So, will this always happen that we can just reverse the order of the partial derivatives? And the answer is, it happens sometimes. So there are conditions under which the order of differentiation and mixed partial derivatives doesn't matter, and so we just saw an example of that. So we have this theorem, but in order to state the theorem, we need the notion of an open disk. So essentially, all an open disk is if you think back to when we worked with an open interval. An interval occurs in 2D space. So it's just on a line, and we have that open interval. An open disk is the exact same thing, except now you have it both in x and y space. So it's just an extension of the open interval that you saw earlier, but instead of it being in an interval, it's now a disk, so it can encompass both x and y space. And so it ends up that if f of xy and its partial derivatives are continuous on that open disk centered at the point x naught y naught, then it ends up at that particular point. You can switch the order of those partial derivatives and you end up with the exact same thing. All right, so as always, if you have any questions, please let me know.